Welcome all. In yesterday's class, we have seen a brief introduction on energy bands and the concept of linear combination of atomic orbitals. So, when the atoms join together to form solids, what will happen? The adjacent atomic orbitals will interfere or will be overlapping. So, the electron is having both particle and wave nature. So, if the electron movement in an atom and the corresponding atom are in phase, then we have one type of orbit known as bonding orbital. And if the electron movement in one atom and the another one is in out of phase, or the phase difference is there, then the particular type of orbit is known as bonding orbital. So we have seen the amplitude in a bonding orbital will be more than the amplitude in a anti-bonding orbital, and the probability of finding an electron in bonding orbital will be more than the anti-bonding orbital, and the energy level in the bonding orbital is less than the anti-bonding orbital. So we have seen the example of hydrogen atom, and we have seen the wave function also in the last class. So we can see here the wave function of one particular atom is psi 1 and the wave function of another one is psi 2. Okay, psi 2. So this is the case when it just started overlapping, or it is not having interference. In that case, it's like this. So you can see when the interference is bonding orbital, or the wave function of both the electrons in the outermost orbital are in phase, then the bonding is known as bonding orbital. So you can see the amplitude will be increasing, that is psi 1 plus psi 2. That is the second case. Okay, and when it is of outer phase, anti-bonding will happen. That time we have a planar node here, has zero crossing is present there, so positive and negative. So this figure gives the bonding and anti-bonding orbital. Atomic orbitals, this is anti-bonding orbital and this is bonding orbital. Here the amplitude will increase, and here the amplitude will increase, here the amplitude is reducing. Okay, so here it's written linear combination of atomic orbitals when two atoms are brought together leads to two distinct normal mode, a higher energy anti-bonding orbital and a lower energy bonding orbital. The second figure gives the electron in the potential well. We can see here, we have seen yesterday the energy level of silicon atom. Same way, if I am drawing the energy level of hydrogen atom, it will be like this. This is a nucleus and only one s level. Atomic number of hydrogen is 1, so the energy level is only 1s. So this is the energy level of first hydrogen atom, and this is for 1s level of nucleus, second hydrogen atom. So what will happen if these two atoms are brought together? When these two atoms are brought together, the figure is shown here. The overlapping of orbital will occur. So you can see here, this is the first one, first HA, having energy level 1s. This is the second one, having 1s level. Okay, so this gives the you can see here, note the electron probability density is high in the region of the iron cores, and if instead of two atoms one bring together n atoms, there will be distinct LCAO and n closely spaced energy level. So you can see here the energy level of both is shown here. Okay, so there will be two energy level, one is anti-bonding energy level, another one is bonding energy level. So this figure is the continuation of this figure. Here we have seen the silicon structure. Energy levels in the Coulombic potential level of the nucleus. Okay, this is for the silicon, and one which I have drawn now is of hydrogen. Okay, this is of the hydrogen. So anti-bonding orbital and bonding orbital. Next we will see the most important topic, that is energy bands, how the different energy bands are formed in this atom or solids. So exams and all question may ask like explain the energy band of silicon or carbon, like that question may ask. So once again I will give the points under energy bands, then we will draw the energy band diagram of silicon and carbon. So energy bands, as isolated atoms are brought together to form a solid, the electron wave function begin to overlap. So various interactions occurs, and at proper interatomic spacing for the crystal, the forces of attraction and repulsion find a balance. Due to Pauli's exclusion principle, the discrete energy levels of individual atom split into bands belonging to pair instead of to individual atom. So when both the atoms brought together at a particular equilibrium condition or the proper interatomic space, what will happen? Due to the Pauli's exclusion principle, state that discrete energy level, now they have discrete energy level like 2s, 2p, like 3s, 3p, 3d. They are distinct energy levels, right? Different energy levels of individual atom that will split into bands, into not a single energy. It will consist of many number of energy. It will be having bands of energy belonging to a pair. That it will be a pair that will be common for a pair of atom, not for the individual atom. So we can see for a particular atom we have 3s, 3p, 3d. So there are three distinct layers, that is 3s layer, 3p and 3d, that will be split into many bands, and that bands will belong to not a single atom. It will be common for a pair of atom. So in a solid, due to large number of atoms, the split energy levels for essentially continuous band of energy. So in order to form in order to form a solid, not even a single atom or a 2 or 3 atom is not enough. There should be many atoms joined together to form a crystal lattice. A lattice structure will be formed that will be called as a solid. So in order to form a solid, large number of atoms are there. So this different split energy levels form a continuous band of energy. So you can see for this figure gives the energy band of carbon. So I can tell you, so I'll draw this for you. Let this X line be the interatomic spacing. Okay, so what is the atomic number of carbon? Atomic number of carbon is 6. So I can write 1s2, 2s2 and 2p2. This is the atomic number of carbon. Okay, so this 1s level is close to the nucleus. So it is close to the nucleus. So this far band will be 2s and 2p. So I will be explaining about that. So this is the 2p level and this is the 2s level. So this is the interatomic spacing. So the interatomic spacing between two atoms. Okay, when two atoms are brought together, what will happen? At a particular distance, this energy level 2s and 2p will split into 2. 2s and 2p levels split into 2. So in 2s level, how many electrons are there? Now in 2s level, 2 electrons. And 2p, in p level normally 6 electrons will be there, but in the case of carbon we have only 2 electrons. This is the case of a single atom. If we are speaking about many atoms, we can tell in 2s orbital, in 2s orbital we have 2n number of electrons, and 2p we have 6n number of electrons. So in 2s we have 2n number of electrons, and 2p it can occupy up to 6n number of electrons. But for the carbon we have only 2 electrons in an atom. So it will split and merge together. Here. Okay. So as the interatomic space decreases further, what will happen? Once it reaches the equilibrium state, the band will again split. It merges and band will again split. Okay, once again I'll explain. So this is the interatomic spacing, and this is our 2p and 2s level of carbon. Below this we have 1s also. Let it be there. This is 1s, 2s and 2p. Okay. So as the interatomic space decreases, as the interatomic space decreases, these 2s and 2p level will split like this and merges as a single band. So you can see this 2s and 2p, these energy levels split into bands, and the 2s and 2p bands merge into a single band. So as I told, in this 2s there will be 2n available states, and in 2p we have 6n available states. So as the interatomic space decreases, these two band splits into bands of energy and they merges, 2s and 2p merges, and here we have 8n electron states. So there 8n electrons can occupy the band now. Okay, so once the equilibrium occurs, once the equilibrium condition is attained or the proper interatomic space is achieved, what will happen? The bands will again split. The bands will again split like this. Bands will again split, and there will be a difference here. You can see a difference between the band. That band difference is given by Eg. So that is the forbidden energy gap. Eg is nothing but the forbidden energy gap. And the top band is named as conduction band. Conduction band. And the bottom band is known as valence band. So when the different atoms interact together to form solids, what will happen? The far away energy levels like 2s, 3s, like that levels, when the interatomic space start decreasing, what will happen? These energy levels split into bands, and the 2s and 2p bands merge into a single band having 8n available states. So here you can see with the reduction in interatomic spacing, these energy levels split into bands, and the 2s and 2p bands merge into a single band having 8n electrons. So before that we are explaining it for the carbon. So carbon electronic configuration is 1s2, 2s2, 2p2. Each atom has 1s2 1s states, 2 2s states and 6 2p states. Okay, normally for all the atom it is like this. For carbon, in 1s states all the 2 electrons are filled, 2s also 2 electrons are filled, in 2p out of 6 2 are filled. So for n atoms we can write it as 2n, 2n and 6n. Okay. So as the interatomic spacing approaches the equilibrium spacing of diamond crystal, this band splits into two bands separated by an energy gap Eg, where no allowed energy states for electron exist. Where no allowed energy state for electron exist, and it is known as forbidden gap. So the upper band called conduction band and lower band is known as valence band. So we have seen that the two energy states 2s and 2p and 2s merge together and having capacity of 810 electrons, right? So this has been separated into two bands. One is conduction band, another one is valence band. So here 8n states are there. So 8n electrons can occupy either in the conduction band or valence band. But at room temperature 0 Kelvin, these 8n electrons will be occupied in the valence band. So the upper band called conduction band and lower band is called valence band, containing 4n states each. So out of 8n, 4n states in the conduction and 4n in the valence band. The lower 1s band is filled with 2n electrons. Okay. However, the 4n electrons residing in the original n is equal to 2 state will occupy either in the valence band or in the conduction band. So we know the atomic number is 1s2, 2s2, 2p6. So generally, so in the last video we have seen the energy band of carbon, but in the textbook we have energy band of silicon. So in this video we'll be explaining the energy band structure of silicon. You should know how to draw this. Okay, so these all things now you leave. Okay, so this figure is drawn with x-axis. X-axis is nothing but the interatomic spacing. X-axis is the interatomic spacing. So we know the atomic number of silicon is 14. So what is the structure? 1s2, 2s2, 2p6, 3s2 and 3p2, isn't it? So altogether is 6 plus 2, okay, 14. Okay, so this 1s, that is the inner shell, and 2s and 2p are the middle shell, 3s and 3p are the outer shell. That is given here, middle, inner and outer shell. So these two shells, inner and middle, which is close to the nucleus, they are tightly bound to the nucleus. So if there are any changes in the energy level happening there, then the interatomic spacing should be that much very small. So the two orbits or n orbits which are bringing close together, very much close together, then only the energy levels will start changing in the inner and middle shell. So we are speaking now about the outer shell. So you can see here this 3s and 3p are the outer shells. Okay, so 3s and 3p are the outer shells. Okay, then so this is the interatomic spacing. This is the relative energy of electron. So what is the, how many electrons a 3s orbit will carry? In 3s, a maximum of 2 electrons will be there. And in 3p, a maximum of 6 electrons will be there. Okay. So in the case of n atoms, 3s can occupy 2n electrons and 3p can occupy 6n electrons or 6n states. But for the silicon atom, we have 3s2 and 3p2. So in this 3s state, we have 2n electrons, and in the 3p state, we have 2n electrons, 2n and 2n. In 3p, maximum 6 electrons can be occupied, but only 2 electrons are there for a silicon atom. So once the interatomic space start decreasing, what will happen? These energy levels will split into bands. These energy levels will split into bands. So this 3s and 3p will merge together. So in 3s, 2n states, 3p, 6n states. So altogether there will be 8 states. When they merge together, there will be 8 states. Okay, so here total 8 8n states are there. So when the interatomic space is further reduced, an equilibrium condition will attain where the force of attraction and repulsion will be balanced. Okay, so that time this will split again. The band will split again into two bands. The upper one is known as conduction band and the lower one is known as valence band. So there are 8n states altogether. There are 8n states. So there are altogether 8n states. So 4n states will be given for the conduction band and 4n states will be given for the valence band. There will be a region where there is no band of energies present. That is known as forbidden gap. And the energy of that gap is known as Eg. Once again we can give a definition for forbidden energy gap, that this is the energy that is required for an electron from the valence band to reach the conduction band. Okay, this is the energy. Eg is the energy required for a electron to reach conduction band from the valence band. That is known as the forbidden energy band, and that value, band gap energy, is given by Eg. So as I explained, in this merged condition we have 8n states. So 4n is given for the conduction and 4n is given for the valence band. For a silicon atom, how many electrons are there in the 3s and 3p? 4 electrons, right? 3s2 and 3p2. So 4 electrons. For n atom, 4n electrons. In the valence band we have 4n states. In conduction band we have 4n states. These 4n electrons or 4n electrons will be occupied in the valence band under equilibrium condition or under 0 Kelvin. These 4n electrons will be filled in the valence band and the conduction band will be empty. Once there is a thermal excitation or optical excitation happens for the solid, some electrons in the valence band will jump or will move to the conduction band. Even if the energy is above the forbidden energy, e.g. the electrons from the valence band will move to the conduction band for participating in current conduction. So this is the energy state diagram of a silicon atom. So I hope you understood this one. You have to draw and study this one. So this figure is drawn with interatomic space in the x-axis and relative energy of the electrons in the y-axis. So this is 3s, 3p. It will split into two bands. Then it will merge at the interatomic space. Again it will split into two bands. One is conduction band, another one is valence band. You go through the videos which I have sent, and if you have any doubt, tell me. Okay, thank you.